Topic of this lecture is sequence of functions part 2. We'll cover these points in this lecture: theorem number 1, example number 1, example number 2, and theorem 2, that is Cauchy criteria. So let us see the statement of theorem number 1. Let the sequence of function f n x converges pointwise to fx on E. This is the first thing. And if Mn is denoted by supremum of all x belongs to E, modulus of fnx minus fx, that is the definition of Mn, then the sequence fnx converges uniformly to fx when it will happen if and only if limit n tends to infinity Mn is equal to 0. So this theorem we will have to prove in two parts. So let us start the proof. From the definition of Mn, this is the definition Mn, we have modulus of fnx minus fx is less than or equal to Mn. This should be less than or equal to Mn for all x belongs to E. Why this is so? Because Mn is defined as a supremum of this. So if limit n tends to infinity Mn is equal to 0, that is our this supposition is this, then given epsilon greater than 0, because of this we can find an n such that modulus of Mn, which can be written as Mn minus 0, modulus of Mn minus 0 is less than epsilon for all n greater than equal to n. It should be greater than or equal to. Hence, because of this one, that this is less than or equal to Mn and the Mn is less than equal to epsilon, we have modulus of fnx minus fx is less than epsilon whenever n is greater than equal to n or all x belongs to E. But this is the definition of uniform convergence. So we conclude that fn converges to f uniform. So this is the first part. Now for the second parts, conversely, let us suppose that fnx converges to f uniformly. This is our supposition now. Then by definition, given epsilon greater than 0, we can find a value n such that fnx minus fx is less than epsilon for all n greater than equal to n and for all x belongs to E. This is nothing but it is following from the definition. So because all this expression is less than epsilon by 2, so if we take the supremum, then supremum of modulus fnx minus fx and x belongs to E, that will be less than or equal to epsilon by 2 for all n greater than equal to n. That is Mn, that is the supremum of this expression, is less than equal to epsilon by 2, which is less than epsilon for all n greater than or equal to n. So by definition, this implies limit n tends to infinity, Mn is equal to 0. Because whenever we have to prove that limit n tends to infinity, Mn is equal to 0, we will have to simply prove that modulus Mn, that is same as Mn, it should be less than epsilon for all n greater than equal to some capital N, and that we have found for a given epsilon greater than 0. So this condition we have proved. So because of this, we have proved that limit n tends to infinity, Mn is equal to 0 in this case. In particular, fx is equal to 0, then fnx converges to 0 if and on E, if and only if supremum of this expression is equal to 0, because here we are taking fx is equal to 0 in this case. Now this theorem is particularly useful whenever we know the pointwise limit of sequence of function defined on E. Now let us see an example. Prove that fnx, which is defined by this, converges uniformly on 0 to k, where k is any positive number. So first of all, we will find the limit so that we will get the pointwise limit. Limit n tends to infinity fnx, that is limit n tends to infinity this expression, and it is equal to 0. Therefore, this given sequence fnx converges pointwise to 0 on 0 to k. This is the first thing we have proved. Now let us take Mn, that is equal to supremum of fnx minus fx, and fx is equal to 0. So this is the supremum of x upon nx plus 1. And that it will be maximum of x upon nx plus 1, because we are dealing with the closed interval 0 to k for all x belongs to 0 to k. Then as fnx is continuous on 0 to k, here it should not be continuously checked. And since limit the derivative fn dash x is equal to 1 upon nx plus 1 square, so it is clearly greater than 0 for all x lies in this interval. But this implies that fnx is strictly increasing on 0 to k. Hence, this maximum value of x upon nx plus 1 will be obtained at fn at k, that is the last point of this interval, the last point k. So that will be k upon nx plus 1 for all x belongs to 0 to k. So by this we have got the value of mn, which will be k upon nx plus 1. And when we find the limit n tends to infinity of mn, that will be clearly 0. So as we have proved the theorem in the last slide, fnx converges uniformly on E. So that is the use of the theorem which we have just proved. Note that fnx does not converges uniformly on 0 to infinity, since limit n tends to infinity mn does not exist when x lies in closed interval 0 to infinity. Now let us take example number 2. Let fnx is equal to nx upon 1 plus n square x square when x lies in this interval. This should be x. Show that fn converges pointwise but not uniformly on minus infinity to infinity. So let us find first of all the pointwise limit. Limit n tends to infinity fnx, that will be clearly 0. So fn converges to fx 0 pointwise on this interval. Now we'll find the value of mn, that will be the definition, by definition this. It will be supremum of this value fnx, because fx we have already found its value is 0. But that value mn will be greater than equal to fn 1 upon n, because mn is supremum value that will be greater than equal to any particular value. So in place fn, and we take in particular in place of x, we take the value n, because x lies in minus infinity to infinity. So we take x is equal to n. So it will be the value 1 by 2. So we got that mn is greater than equal to 1 by 2 for all n is equal to 1, 2, 3 and all. It means if we take the limit n tends to infinity mn, that will be greater than or equal to 1 by 2. So this suggests that limit n tends to infinity mn is not equal to 0. So because of this, we conclude that fn does not converges uniformly on minus infinity to infinity, because we require that limit should be equal to 0, but it is not 0. Now let us take this theorem that is called Cauchy criteria. Let us see the statement. Let fn is a sequence of real valued function defined on E. Then fn converges uniformly on E to some function f. If and only if, when this will happen, that given epsilon greater than 0, there exists some n such that modulus of fmx minus fnx is less than epsilon for all mn greater than equal to n and x belongs to epsilon. So this we have to prove that fn converges to f uniformly if and only if this condition is met. So let us suppose first of all that fn converges uniformly to f on E. Then what will happen? By definition, given epsilon greater than 0, there exists some n belongs to n such that modulus of fnx minus fx is less than epsilon by 2 for all n greater than equal to n and for all x belongs to E. So therefore, if the value of m and n are greater than equal to n and any x belongs to E, we can use this expression over here and we find the modulus of fmx minus fnx, which can be written like this, and using triangle inequality that will be less than equal to this two expression, and that too will be less than epsilon by 2 and epsilon by 2 because again using this, and that will be equal to epsilon. So what we have proved, that given epsilon greater than 0 there exists n belongs to n, and we have obtained from here such that if the value of m and n are greater than equal to n, then the value this is less than epsilon, that is written over here, that fmx minus fnx is less than epsilon. So by this way this one part is proved. Now we'll suppose the another part, that is conversely, that fn is a sequence of function on E such that given epsilon greater than 0 there exists some n such that modulus of fnx minus fnx is less than epsilon whenever m and n are greater than equal to n and x belongs to E. This is our supposition. Now we have to prove that fn converges to some f. So we'll have to produce an f. So we'll have to show there exists an f on E such that fn converges uniformly to this f on E. So we'll produce this f. How to produce? We'll use this 1 which is given. So by 1 for each x fixed x belongs to E. Because of this, we get the sequence of real number f and x, which is a Cauchy sequence. Why this is so? Because this criteria holds. Hence, for each x belongs to E, limit n tends to infinity f and x exist. Why this is so? Because Cauchy sequence of real number is always convergent. So let us define this f which we have to construct by fx is equal to this limit. So this we are defining by this way the fx. Now once we have defined this, now using this expression, taking m fixed in this expression 1 and letting n tends to infinity over here, we get that modulus fmx minus fx, which is equal to this limit, that is less than epsilon for all m greater than equal to n and for all x belongs to E. So, and as epsilon greater than 0 is arbitrary, so this second implies by definition that sequence fn converges to f uniformly on E, because recall that fn converges to f uniformly. What we require, that given epsilon greater than 0 there exists some n such that if n or m, we can say m, if m is greater than equal to n, then greater than or equal to, then this should implies modulus of fmx minus fn fx, it should be less than epsilon, and that we have just proved over here. Here this epsilon should, the value of n should depend on epsilon only, and it should hold for all x. So this we have proved. So by this way fn converges to f uniformly on f. So by this way this theorem is proved. So you can find the link of this PPT in the description box. Thank you very much.